Alright, now we're going to take a look at some of the factors that affect reaction rate. So we've looked at reactions and the rate at which they occur and rate constants. So the rate constant lets us see how the rate is affected by different concentrations, and also lets us determine what the rate is at any given point in time or any given concentration. But in order for that constant to stay constant, we have to keep the conditions the same. So here's kind of a look at the conditions that would affect the reaction rate. So some things that we can do to change the rate. So here they are, the rate of collisions between reactants. That's going to affect how it reacts, the percentage of collisions with an orientation that could produce a reaction, and the percentage of collisions possessing sufficient energy, the activation energy as we're going to talk about, to produce a reaction. So we'll go through and look at each of these three and why it is that they affect the reaction rate. So first off, the collision rate. So let's think of just a general reaction where, let's say, A and B react to form a molecule that we're just going to call AB. So in order for that reaction to occur, you can't just have molecule A sitting over here and molecule B sitting over here, and then they just magically form AB. They actually have to hit each other in order to form that compound. So that's what a collision is. It means A bumps into B or B bumps into A, and that's what causes the reaction. So they have to come in contact with each other. So collision rate, what are ways that we can increase collision rate? We can increase the chance that A is going to meet up with B. Because if we have a huge container and a single A down here and a single B up there, what are the chances those two are going to run into each other? What are ways that we can increase the chance that they'll run into each other? So the first thing we can do is we can increase the concentration of the reactants. So if we have a lot of A's and a lot of B's, the chances of them bumping into each other are a lot greater. And so by increasing that chance of bumping into each other, we increase the rate. If we decrease the concentration, we decrease the rate. Also, temperature. So remember, temperature, kinetic theory, as you increase the temperature, you increase the movement of the particles. And so when you increase that temperature, they move around faster, and so they have a better chance of bumping into each other. A third way that's not listed on here is, a pretty common one, and that's just mixing. Okay, if you mix up a solution or if you mix up a reactant, you're getting the increase in the chances of them hitting each other. Otherwise, they might just chill on their own sides of the container and never really come in contact. So you're kind of finding ways to bring them together. Let's use the analogy of trying to find a date to describe this. So most of you guys are probably trying to find a date, and as the concentration of the reactants increases, so if you want to increase your chances of finding a date, you hang out with more of the opposite gender. If you're just with one other person or two other people, you might not find the right one. But if you're in a room with 100 of the opposite gender, you're increasing your chances of finding someone and forming that compound. Temperature increases. Remember, temperature increases the motion. And so if you increase the temperature, you're increasing how much you're moving around. And if you're moving around more and more and more, you have a better chance of bumping into someone. As opposed to if you're cold and just stand still, and all of the opposite gender is over in this corner, you're probably not going to bump into them that way. And last thing is mixing. So mixing and mingling throughout the crowd, you're going to increase your chance of finding someone while you're out there. Something to note that not every collision triggers a chemical reaction. So not every girl that you meet is going to end up being a date. Not every A that bumps into B is going to form an AB. They have to hit with a proper orientation and a proper speed as well. So here's what I mean by that. If you take a look at this little setup right here, it shows NO2Cl reacting with itself. So we have two of them bumping into each other, and that's going to form nitrogen dioxide and Cl2. So if they bump into each other, as shown in this diagram right here, where we have the oxygen bumping into the Cl and the O bumping into the O, that's not going to form a reaction, because if we look at our products, we need to form a Cl2, which means this chlorine needs to come in contact with this chlorine. So bumping in this orientation is not going to form a reaction. Even though they're hitting each other, the two molecules that need to react are meeting, they're not meeting under the proper conditions. In order for reaction to occur, it has to occur like this, where Cl matches Cl, and that'll give us our nitrogen dioxide, and Cl2 as shown in the balanced equation. So not all collisions actually produce a reaction. And it depends on the shape of the molecule, because if you look at this, there's a lot of space over here and only a small area that can actually come in contact with each other. So the chances of these two bumping each other might be tricky, and that's going to create a slower reaction rate. So the reason some reactions occur slower than others might be because the orientation that they have to hit with is very, very precise. So another reason why a collision might not produce a reaction, and that's because of the activation energy, which is symbolized with E subscript A. So activation energy is the amount of energy required to activate a reaction. So if we look at just this general example, AB is reacting with C to produce A and BC. In order for that to happen, AB has to bump into C. And when it bumps, it's going to have enough energy to break apart its bonds and then form into A plus BC. So basically, C has to hit AB with enough force to overcome A's bonds, send it packing, and itself join on with BC. If it just kind of lightly taps into that guy, well, A's just going to knock it off. So it'll just ricochet off and have to go find someone else. In order for the reaction to occur, the activation energy, so the amount of energy required to activate to cause this reaction, has to be less than the energy of the collision. So the energy of the collision has to be greater than the activation energy. So the energy at which these two hit has to be greater than this amount of energy right here. A way we would have seen this is with methane. So our Bunsen burners we would have seen this with. If you think of just butane, so methane, that comes out of our Bunsen burners, it reacts with oxygen to produce CO2 plus H2O. That's not balanced, but we just want to look at the equation anyway. So CH4 reacts with oxygen to produce carbon dioxide and water. So if there's oxygen already out in the atmosphere, and we turn on our Bunsen burner, why is it that when we turn on our Bunsen burner, and that CH4 is coming out, mixing with the oxygen, that those two don't react? And it's because of this. There's not the energy to produce that collision that causes the reaction to occur. So we need some way to give it that energy to cause the reaction to actually proceed. So what do we use to trigger this reaction? What do we use to spark this reaction? We use a flame. And so what that flame does when you take a lighter and you pull it over your Bunsen burner is you are giving it the activation energy it needs so that this collision right here can have enough energy to form CO2 and H2O. And once you have that collision happening, obviously this produces heat, and that heat actually acts as the activation energy for the other molecules that come out. And so it triggers its own reaction, but you have to give it that initial kind of push to get over that hill so it can start producing its products. Otherwise, the Bunsen burner is just going to keep running, spilling out gas, but those two will never react until they have enough energy. So here's what would happen if it didn't have enough collision energy. So we think of this same reaction right here. We have A and B reacting with C. So we can see from the products that C is trying to attach itself to B. So, if these two just bumped into each other, what might happen is A would stay attached to B, and then B would hold on to C. So B kind of bumps into C, clicks onto it, and it's like pushing a cart slightly up that hill. So it would go up this hill, but if it doesn't hit with enough speed, then it can't really throw that A off the other end. And so what will happen is it will form into that when they bump into each other. It'll go up, but then it'll come back apart. It doesn't have enough energy, and so C will slip back off and go cruising until it finds someone else. So it needs to have enough energy, and we can give it that energy by heating it up so that it's moving faster and the collisions will hit harder. And with a harder hit, then it's more likely to knock off A and give it that activation energy that it needs to form the products. So the value of activation energy can change depending upon the reaction or how we set up the reaction. Generally, a slower reaction will have a higher activation energy. That's why a reaction occurs slower, because it requires more energy to get over that hump and form your products. A faster reaction, one that's really, really quick, usually has a really low activation energy. So it doesn't take much to get it going, doesn't take much to get it over that hump. So this reaction right here, if it had a large activation energy like that, would occur pretty slow. And then a reaction like this would occur pretty quickly because it's got a lower activation energy. So a good thing to think about then is if we are looking at a reaction and it's an extremely slow reaction, you could hypothesize, and you'd probably be correct, that it has a high activation energy. Whereas if we were to look at a different reaction and its rates, we were to see that it had a pretty quick rate, we could hypothesize then it has a lower activation energy. And so here's 3 take-home points that I'd like you to know about reaction rates. So in order for a reaction to occur, we've got to meet 3 conditions. There must be a collision. And the collision has to occur with a proper orientation that would yield the reaction, so the things that need to combine need to hit each other. And the energy of the collision has to be greater than the activation energy in order to overcome that hump.